Hello students, welcome to the course on Hydrology EVE 301 offered to civil engineering students at College of Science and Technology. I am Kirtan Adhikari, faculty at CST. See you in the course. We shall continue our discussion on abstraction from precipitation or losses. The third and the most important abstraction is the infiltration, which is defined as the entry of or the passage of water into the soil surface. The maximum rate at which water is absorbed by the soil at any given time is known as infiltration capacity. Understanding infiltration is very crucial in hydrology, as infiltration is the major loss from the precipitation and it adversely affects the magnitude, the timing, and the distribution of surface runoff at basin outlet. Let's understand more on this topic with this short animation from Comet program.
Infiltration rate is the amount of water able to enter the soil in a specified time period. It is expressed as depth per time, for example, 10 millimeters per hour. Infiltration capacity is the upper limit of infiltration rate. It includes surface infiltration and percolation and is expressed in depth per time, for example, 15 millimeters per hour. If precipitation rate is less than or equal to infiltration capacity, no surface runoff occurs. If precipitation rate is greater than infiltration capacity, surface runoff occurs. Surface runoff equals rainfall or snowmelt rate minus infiltration capacity. For example, if our rainfall rate increases to 25 millimeters per hour, but the infiltration capacity remains at 15 millimeters per hour, then the rainfall rate is 10 millimeters per hour greater than the infiltration capacity. The 10 millimeters per hour that does not infiltrate becomes surface runoff.
I hope now you can visualize how infiltration affects surface runoff. In this lecture, we shall model the infiltration mathematically to predict the surface runoff generation quantitatively. The illustration on the right shows a soil column and various zones indicating the distribution of soil moisture within the soil profile during the infiltration process. During a rainfall event, the topmost layer remains saturated and the infiltrated moisture proceeds to a transition and transmission zone. The moisture continues to move downward till it reaches the most saturated zone. And when the process is prolonged, the groundwater table rises. Infiltration continuously affects the magnitude, timing, and distribution of surface runoff as demonstrated in the animation. During any storm, infiltration is maximum at the beginning of the storm. It decays exponentially and attains a constant value as the storm progresses. With this, let's understand the effect of infiltration. It reduces flood magnitude. More infiltration means less surface runoff. Likewise, delayed time of arrival of water to the channel. Reduce soil erosion. Recharge to the groundwater reservoir. Fills the soil pores with water to its fill capacity, which subsequently supply water to the plant, as it is responsible for growth and nourishment of plant, as soil moisture is recharged continuously through the process of infiltration. There are various factors that affect infiltration and some of them are listed here. As you can observe that in the beginning of a storm, the infiltration rate and the initial loss rate is significant. At this time, the runoff is negligible. With the progress of time, the infiltration decreases following a decay curve. Similarly, the initial losses too decrease. The initial loss decrease swiftly compared to the infiltration. Gradually, runoff starts to build up at the basin outlet. As the volume of water in the catchment drains into the channel, which gradually increases the discharge at the basin outlet. The runoff continues to increase even after cessation of rainfall as water takes time to travel to the outlet. The runoff finally reaches its peak and then gradually decreases. Further, let's discuss on the measurement techniques, the measurement of infiltration, the techniques used to do the field measurement of infiltration. The equipment used to measure infiltration is known as infiltrometer. There are two versions of infiltrometer: single ring infiltrometer and double ring infiltrometer. Single ring infiltrometer or simple infiltrometer consists of a tubular cylinder with 30 centimeter dia and 60 centimeter long, open at both the ends. The cylinder is driven into the ground to a depth of 50 centimeter. Water is poured into the top cavity to a depth of 5 centimeter. Volume infiltrated is recorded with respect to time. More water is added as water infiltrates. Whereas double ring infiltrometer also operates similarly to that of the single ring infiltrometer. However, double ring infiltrometer consists of two concentric cylinders with diameters of 30 centimeter and 60 centimeter and of minimum length of 25 centimeter. The water depth in the inner and the outer ring are kept at the same depth during the observation, but the measurement of infiltration is done on the inner ring only. Since the vertically infiltrated water tends to flow in all directions, the outer ring of double ring infiltrometer serves as a separation. Thus, the measurement exclusively takes place in the inner ring through which the water runs vertically. That is the advantage of double ring infiltrometer. The data we get from infiltrometer will be in a form of a cumulative curve. The slope of this curve at any point gives us the infiltration rate. With this, let's continue with the models to represent the infiltration mathematically. There are many infiltration models available in the literature, such as Horton's model, Phillips model, Custia-Cove model, and Green-Armt model. However, we will only focus on Horton's model. Horton, in the year 1933, gave an expression to model the infiltration, and his expression is the infiltration capacity is equal to, at any point, is equal to the final steady infiltration rate plus the difference of final and initial infiltration multiplied by the exponent raised to power a coefficient times multiplied by time. Okay, so this is the expression to model infiltration given by Horton. You can see this image. If this is the rainfall pulses, which we also call this as hydrograph, and this would be the shape of infiltration at any point of time, and maximum rate of infiltration at any point of time is known as infiltration capacity. So this function is a function of time that gives the infiltration capacity with respect to time, and the amount of rainfall that is infiltrated is the infiltrated rainfall, and the remaining rainfall is known as effective rainfall, and this effective rainfall is responsible to generate surface runoff, as you have already seen in the animation. Now question comes, how to compute the values of the decay exponent of this decay constant if we have the data from infiltrometer. So for this, what we do is we take this fc to other side, and becomes capital F of t minus fc is equal to this expression. And now we take the logarithm on both the side, and we get this expression. If you look closely, this expression is in the form of y equal to mx plus c. In fact, it is y equal to mx minus c, where minus c is equal to the slope of the line that we are going to get from this, fitting this values, okay, fitting this into a chart. So that's how we get the value of minus k, or the decay coefficient. Once decay coefficient is known, the initial and final value can be directly read from your observation data sheet, and then we can finally fit a infiltration model using Horton's equation. With this, let's try to solve a numerical. The infiltration capacity of a catchment is represented by Horton's equation as the infiltration capacity at any point time t is given as 0.5 plus 1.2 exponent raised to minus 0.5 t. So if you notice, this minus 0.5 is the decay constant, where f of t is in centimeter per hour and t is in hour. Assuming the infiltration to take place at capacity rate in a storm of 4-hour duration, estimate the average rate of infiltration for the duration of the storm. So if I just go back to refer the image, you can see here, this is the equation that is given to us. Now it wants us to find the average infiltration. Now average infiltration would be the total infiltration, right? Total infiltration divided by the total infiltration divided by the duration. Total duration would give us the average infiltration. So to find the total infiltration, what we do is we integrate this from 0 to 4 hour. In the question it says it's 4 hour, right? This storm lasted for 4 hours. So what we do is we integrate this equation from 0 to 4 hour, and then divide it by total duration. So let's integrate this. So it would be 0 to 4, integration of 0.5 plus 1.2 e minus 0.5 t. So I have done the integration, and the value is 4.075. So average infiltration is going to be total infiltration divided by duration. Duration is given as 4 hours. Then we get 1.02 centimeter per hour. So this is the average infiltration. With this, I would like to end this lecture.